Hello, everybody. It is April 14th, 2020. We're about a month into the coronavirus shutdown. So I thought, since I can't give in-person seminars, that I could record this and distribute it that way. So maybe people will have a little downtime and want to watch something other than read about the coronavirus. Okay, let's get started. I'm sharing my screen with my slide presentation. All right. So today I am going to talk about a home project that I did that is to use neural networks to see if the neural network can learn from many training examples how to solve for atomic structures based on X-ray diffraction data. This is kind of a problem that's been addressed for many years, and there are many means of doing this, but typically it involves doing extra experiments to collect more data, because the data that you get from the original experiment is often not sufficient to solve for the atoms, the atom positions. Okay, I'm just going to keep going through this, even if I kind of stumble on my words a little bit. So now I'm talking about X-ray diffraction data, but there's this kind of simple transformation that you can make to convert X-ray diffraction data into a Patterson map. So that's why it says from Patterson maps to atomic coordinates. And I'm working on a kind of simplified case where I'm just trying to train the network I'm training the network on 10 random atom positions, and then I'm seeing if the network, when presented with diffraction data from 10 random atom positions, can generalize and learn for cases that were not in the training set. I'm going to discuss this much more as we go, and including an introduction to everything that I'm mentioning. This work is my personal project. The opinions expressed in this presentation are my own. They do not reflect the view of the National Institutes of Health, the Department of Health and Human Services, or the United States government. So in other words, I did this as a home project. And I did that because I haven't had opportunity at work to work on deep learning projects. And I can see that it's obviously a hugely important and direction that I would like to go in. So I've actually worked on two deep learning projects now. The first one was I was trying to see if I could train a neural network to run a molecular dynamics simulation. And I had some success with that, though I can't get it to go for long trajectories. But then when I was set up with that, I thought, well, it's not so hard to use the very same training data to see if I can create, to create diffraction data on the neural network input rather than time steps from the molecular dynamics simulation. So I have written a paper about this work, and that's the link for this paper. It's on arXiv. Oh, one other thing I want to say is these images that are in the introduction are not mine, and I'm crediting them, on this small font line on the very bottom of the screen. So this is a Patterson map. This is it's showing atomic coordinates, and this is a neural network schematically in the center. But this paper that I'm crediting is not a deep learning paper. It was just something I took those images from. All right, here's the introduction to this talk. First, I will discuss the phase problem and what the Patterson maps are. Then I'll discuss about neural networks and convolutional neural networks, and that will all be introductory material. And then I'll get to the subject of this work, which is training the neural network on the Patterson maps as inputs and atomic coordinates as outputs. All right, the phase problem. So generally speaking, when you want to solve for the structure of a protein or DNA or some biological macromolecule, what you need to do to use X-rays is to first grow a crystal of the protein so that you have a repeating unit of the protein. Then that crystal is placed in the path of the X-ray beam, and the crystal will diffract. I mean, if the crystal, not all crystals will diffract, but if you're lucky, the crystal will diffract. And you can then collect the intensity information from each of those little rays from the diffraction pattern. So the way I think of it is like the crystals in the path of the X-ray beam, and then you get this like disco ball, kind of these small X-ray beams are coming out in all directions. And that's a diffraction pattern. So, you know, like with light microscopes, you would use a lens to focus the image, and in an electron microscope, you would use magnets to focus the image. But in X-ray crystallography, there's no way to focus the X-ray diffraction pattern. So what you need to do is do it computationally. That's what is done. And then there's certain information missing. So it would be very straightforward to calculate the electron density map from this diffraction pattern if you had the full set of data that was that was diffracted. But some of the information cannot be recovered. So when the diffraction experiment is done, you can measure the intensities of each one of these pieces of the diffraction pattern, but you can't measure the phases. The phases are gone. There's no way to recover those. And so that's why this is called the phase problem. So absent the phases, you would still like to know what the molecule looks like. And so, like I said, there are different techniques that are used to do it. And most of those techniques involve getting more phase information. So some of the techniques are like there's a molecular replacement, single wavelength anomalous dispersion, multiple wavelength anomalous dispersion, multiple isomorphous replacement. And then, so it's a little more complicated than just going straight forward from the diffraction pattern to the electron density map. But it can be done, and it has been done many times. And then from the electron density map, you can create an atomic model. And actually, in the protein data bank, the vast majority of the protein structures in there are from X-ray diffraction experiments. So something like 90% of the protein structures that are in a protein data bank are from X-ray diffraction experiments. But there are other techniques. There's NMR, nuclear magnetic resonance, and then there's also, of late, a very important technique that's been used is cryo-electron microscopy. And there's been a huge improvements in cryo-electron microscopy in the last decade. And there's this so-called resolution revolution. So it used to be that if you wanted to solve a protein structure down to atomic resolution, you really X-ray diffraction experiments were the best way to do it. But now there have been cryo-EM structures that have been also solved down to atomic resolution. Okay, this talk is not heavy on math, but what I want to show here is that this FHKL, these are the reflections. So each one of these dots is called a reflection. And if you do a Fourier transform on the reflections, you can recover electron density. But in order to do that, you need magnitudes and phases. But the phase information, like I said, is gone. And just for people who aren't familiar with Fourier transform, I'm just giving a little taste of it here. So this is showing summing a number of sine waves and creating a square wave from those sine waves that are being summed. In fact, you can, if you have enough waves, you can create any pattern using a Fourier transform. But you can see here that to do these sharp corners here of the square wave, you need very high waves. So in the same way, you can imagine that to solve an atomic structure to very high resolution, you need the fast changing waves. And each one of these little spots in the diffraction pattern represents a wave. This is actually kind of a three-dimensional wave that it represents. And you see here, these sinusoids are being summed. Now, when I'm talking about the phases, when the X-ray experiment is done, you know the magnitudes of each one of these waves, but you don't know the phases. In other words, you don't know the shift of one sinusoid relative to the other. That's the information that's completely gone when you've collected the X-ray data. So still, like I was saying, there are techniques to recover more phase information, and but there's another technique that is called direct methods that was developed in the 1950s was the start with a guy named Sayre who developed the Sayre equation. And I think that that's what I'm showing here is the Sayre equation. And then Hauptmann and Karl in the 1980s won a Nobel Prize for their work. And the basic idea here is that these diffraction patterns are not, the phases of these diffraction patterns are not just random. There's ways to say that there's a kind of the phase of one is related to the phase of two others. They're so-called phase triplets. And that's the idea here. Here, H, K, and minus H minus K are saying that the phase of one plus the phase of another is approximately equal to the phase of this other reflection. And this approximate can be converted into a probability equation. And then if you have a series of probability equations like that, then you can solve for the for all the phases of the molecule. But the thing is that this actually only works for relatively small molecules of up to a few hundred atoms, and and also it has to diffract to very high resolution. In other words, you need atomic resolution, and not all crystals will diffract to atomic resolution. The principle behind this was that you know, if this kind of a probability equation you can get to mathematically if you assume that electron density is always positive, which is true for a real electron density map, and that the atoms at the electron density has spots in them, or it exists as atoms. It's not just, you know, kind of diffuse electron density, but there are peaks in the electron density map. Okay, now let me say something also about the Patterson map at this point. So like I was saying here, if you know the magnitudes and the phases, it would be a very simple matter to do a Fourier transform and reconstruct the electron density map. But we don't know the phases, so we can't do that. But we do know the magnitudes of each one of these spots. So what you can do is you can do a Fourier transform of just the magnitudes squared, and that will give you a Patterson map. So this is what we would like to get to, but this is what we can get to using the diffraction data. The advantage of using this kind of formulation is that in a way the advantage of using this as opposed to using diffraction data as the input to the neural network is that the diffraction data is in like Fourier space, and it's hard to understand what any one diffraction pattern means. But the Patterson map actually is in real space, and it has a real physical meaning, which I'm going to explain on the next slide. And so taking the X-ray diffraction data and converting it to a Patterson map is, it's just a simple transformation. I imagine that this method would also work if instead of having Patterson maps on the input, you would have the X-ray diffraction data on the input as well. Okay. Patterson map. So what does the Patterson map look like? The Patterson map also has a set of peaks in the same way that the electron density has a set of peaks. However, it has many more peaks. In fact, it has order n squared peaks. And each peak in the Patterson map represents a vector. And they are the vectors between each pair of atoms in the repeating unit of the crystal, or in the electron density map. So let's say that you had, you know, whatever, 100 atoms in your repeating unit, or in the electron density map that you're trying to get to, then there'll be 100 squared peaks in the Patterson map. This is showing what the Patterson map kind of looks like. So you see here, this is just showing 3 atoms, the red, the blue, and the green on the left. And those are then drawing a vector between each one of those gives you the 3 vectors that are here for these 3 atoms. And you see, if you scaled up to more atoms, the number of vectors would increase to, you know, roughly the square of the number of atoms in the density map. So here, this is showing kind of a repeating pattern of the Patterson map, because in the same way that the crystal has a repeating pattern of electron density, the Patterson map also has a repeating pattern. Oh, and one other point that I wanted to make is that mathematically, it is equivalent to say that the Patterson map is the electron density convolved with its inverse. So I don't know if there's this theorem, it's called the convolution theorem. And what it says is that if you do a convolution in real space, that is equivalent to multiplication in Fourier space. So because we're doing a square in Fourier space, that's equivalent to doing a convolution in real space. So this is just to say that doing a convolution of electron density with its inverse will give you the same Patterson map as the way that I had shown constructed on the previous slide. And this is interesting to note because, you know, there are other neural network applications like image sharpening, or sometimes they call it image super resolution, where you take kind of blurry images and you try to create a nice, sharp, crisp image. And that is a deconvolution. So in some ways, this is a problem that has been addressed elsewhere, to do use a neural network to do a deconvolution or a kind of image sharpening. So you could think of this problem as a kind of image sharpening. All right, now I'm switching gears and I'm going to talk about neural networks a little bit. So this schematic here that I'm showing is one unit of a neural network. And people originally thought of neural networks as, you know, something that kind of models a real neuron, where you have different neurons, or I'm not sure I'm using the right term, but like dendrites maybe, feeding into a neuron, and then the neuron behaves as does a summation, and then there's a non-linearity on the output. In any case, neural networks, whether they mimic real neurons or not, it doesn't really matter. They've kind of taken off and they have a life of their own. And but this is still the basics of how neural networks work, and how one neuron of a neural network works, is that there are inputs coming in to a neuron. They're each multiplied by a weighting term. Those multiplications are summed. There's a bias term added here in the neuron. And then on the output, there's a non-linearity that's applied to the output. This is necessary because otherwise all you're doing is doing linear transformations of your input, and you won't be able to do complicated things with your neural network if you don't have non-linearities in it. Anyway, this activation that I'm showing here is called ReLU, which is a very common one. There are many others that are commonly used. There are others that are commonly used. So that's one neuron. And now, when I'm looking at this slide, each one of these dots is kind of one neuron. So here, so this basic unit is inside of each of the dots on this page. And this is what you would call a fully connected network. So each layer, so neural networks are typically composed in layers, and they're repeating, there are multiple layers in the network. And once you get beyond, I think, 3 hidden layers or thereabouts, you start to call this a deep neural network. That's really more branding than anything else. But so in a fully connected layer, each node in one layer is connected to each node in the previous layer, and so on. So this is a fully connected layer. But you can imagine that if you're working, let's say, with a high resolution image and you're trying to propagate that rough image size through the network, it would be just impossible to work with numbers that large, number of weights that are that large, because it would be the square of the image size. So one big advancement that was made in neural networks is this, I got ahead of myself. I'm going to get back to the big advance of convolutional neural networks in a second. First, I just want to talk about another very important advance in neural networks was this idea of learning by back propagating of errors. This citation on the bottom is highly cited, highly used. So the basic idea here is, if you look at the flow of the signal, you have an input coming in on the left, and then these summation and nonlinearities applied in each one of the nodes, and then the image kind of progresses through until you get some outputs on the results on the output of the neural network. But in the reverse direction, you have error signals. So when you're training a neural network, you know in some cases, or for a large number of cases, what the true output should be. So then what you can do is, at any point during your training, to say, okay, I know what the true output is, and I know what the network is producing right now as the output. So let me take the error, the difference between those two, and use that like to feed that error back through the network, so that the network weights can be adjusted. And this is done, can be done millions of times, where you calculate in the forward direction what that network output is, and then in the reverse direction, you correct the weights so that the output that the network is producing is close to the true output. And there's much literature written about how to do that kind of a technique of adjusting the weights, but that gives you a little flavor for it. Okay, this is the other important advance in neural networks. that I alluded to earlier, which is using these convolution kernels. So you see, rather than have each layer, each neuron at one layer connected to each neuron at a the previous layer, what you can do is basically have these convolutional kernels that operate on only a small section of the neural network. So this is shown in 2 dimensions. So here you would have this kernel, this convolutional kernel that would scan over the entire input. And there can be many of these kernels at each layer, but the thing is that the number of weights then is related to the square of the number of weights in the kernel times the number of channels, in one layer times the number of channels in the next layer. A channel is like RGB, red, green, blue. So that would be 3 channels. So there's channels at each layer. And but the key point here is that when you're using convolutional neural networks, the number of weights at any layer is proportional to the square or the cube, if I'm using 3-dimensional space, of the size of the kernel, and not the square of the image size. So it's much smaller number of weights. So the number of weights is much fewer. And this is also was a big advance for working with images. So these techniques have been developed a lot also. But the point I'll make is that, you know, by posing the X-ray diffraction or the phase problem as an image in, image out, it means that we can look to some of these other techniques that have been used on high resolution images and say, well, maybe we can use that technique for this problem as well. And that's what I've done, is use convolutional neural networks for this problem. All right, one more piece of the puzzle. So I mentioned the important pieces of the puzzle of learning by back-propagating errors and convolutional neural networks. Another important advance that's come along in the last decade in convolutional neural networks is to use GPUs. Excuse me. GPUs are used a lot in gaming machines, and that exact same technology can be used for training neural networks. And can be a big performance improvement by training with neural networks with GPUs. And the main point of the GPUs is that they can do the exact same mathematical operation many times at once. So in the same way that they would be used in doing 3D rendering for a game, they can be used in doing the same calculations for training a neural network. So putting it all together, in 2012, there was a big boom in deep learning. And there's this image challenge that's done each year called the Large Scale Visual Recognition Challenge. And what they do at that challenge is give researchers a bunch of images and see how well their software does at identifying what kind of image it is. In other words, there could be like horse and cars and dogs and cats and whatnot. So 1,000 different categories of images. Then everybody sees on these different, million images, how well does their software do at classifying each one of those images. And in 2012, there was a group that managed to put all the pieces that I'm describing together using GPUs, using lots of data, which I didn't get to, but that's also important. Learning by backpropagation of errors and convolutional neural networks. And they made a big advance in 2012. They had a deep neural network that was 8 layers with 5 convolutional layers. They used GPU for training. And many people think of this as the start of the AI boom. They had a big, let me see, I'll go back to this in a second, but they had a big performance increase. See how in 2010, 2011, there were sort of modest performance gains in this ImageNet challenge. And then they came along in 2012 with their AlexNet deep neural network and had a big improvement gain. And then everybody got the idea, like, okay, this is definitely the way to go. And after that, everybody started doing improvements on convolutional neural networks, and the improvement gains continued until, by 2015, 2016, the neural networks were doing this classification challenge just as well as human level performance. So going back here, I'm just making the point that this reminded me in a way of how after the United States Civil War, if you look at bicycle technology, like there's this really terrific exhibit that is at the Smithsonian. Sometimes it's called the History of American Road Transportation. They show you a whole evolution of the bicycle. And you can see how in the 1860s, after the Civil War, there were big improvements. And you had chains that were being used, even gearing, rubber tires. And then finally, like 1890, there's this bike that came out. It was called the safety bike. And it looks very much like bikes that we use today. And I'm kind of saying here that in some ways, I think this AlexNet is like the safety bike of neural networks. They just put it all together and made something that functions well. And the neural networks that many people use today resemble in many parts the AlexNet of 2012. Okay, I am going to take a little break. So I think the best way for me to do that is end the meeting right now. And I'll come back.